analysis. Because it's white flange, we're only going to consider Q. Okay, box beam is 2Q, right? You look at down here, box beam, you have a terminal, one Q go towards the left, the other Q go towards the right, that's why it's 2Q. Whereas this white flange, if you look at this section, you only have Q on the right hand side, you also have Q. They are independent. That's why if you look at the textbook properly, they call it Q1 and what? Q2. Okay, they're independent. Right, coming back to our problem now. So from here, what is the area to consider? Okay, so the area is relative from the what? Terminus. I repeat again, the area to consider is relative to the terminal. So I'll put down here the area of consideration is relative from the terminal. Okay. So for this case, at point A, we are only going to consider this area over here. Okay. From the terminal. Okay. So regardless of the Q direction, everything is from the terminal. Okay. So from here, we're going to find the shear, the first move area at point A. Okay. So this is equal to width, depth, y bar. So the width we know is equal to 0.7. The depth is 0.2. The y bar is 1.5 minus 0.2 divided by 2. So this is equal to 0.7 times 0.2 times by 1.4 is equal to 0.196 inches cubed. Let me do it again. So 1.4 times by 0.7 times by 0.2 is equal to 0.196 inch cubed. So now we can find the shear stress at point A, right? So this is equal to V over I are constant, regardless of whatever point we're interested. The Q is 0.196. Now, over here, you only need to divide by the thickness. Over here, the thickness is equal to 0.2. Divided by 0.2. Okay. You don't, and you just, I put 1 down here because we only have what? Q. Okay. Now I'm teaching, I put 1. In reality, you don't need to put 1 at all. Okay. I'm just teaching away. So this is equal to 0.196 divided by 0.2 is equal to 0.98. So what we realize, the shear stress at point B and the shear stress at point A are the same, right? If you look at the V over I ratio multiplied by 0.98, the coefficient for at point A and at point B, they share the same coefficient. Both of them are 0.98. Okay. So now, next we're going to determine the first moment of area at the centroid. Okay. So we're going to determine the first moment of area at the centroid now. Okay, because we know that at the centroid, the first moment of area is going to be at its what? Maximum. Okay, so this is our centroid. Okay, this is our centroid. Okay, so I'm going to show 2 ways of doing this. We can use either the top or the bottom. If the analysis is done correctly, the answer should be the same. Okay, so we are going to find, I'm going to call this point point C. Okay, we're going to find at point C what is our first moment of area or our shearing stress. Right. So we are going to find the shear stress at point C. Right. And we know that this is a box beam analysis. Right. It's because we have one terminal over there, then it splits into left and right. So this is a box beam. So we know that this is going to be 2Q, right? 1Q go to the left, 1Q go to the right. Okay. Then from here, we also know that the thickness at point C is 0.3 inch. Okay. So the first moment of area of point C is equal to, so I'm going to divide it this way. The area that we're going to divide is, we're going to divide the area this way. So this is the flange, and the other shading direction, that is our web. Okay, so I'll call this our flange. So this is our web. We did our calculation of our flange. So Q of flange plus by the Q of the web, right? So this will be equal, so the width is equal to 2 minus 0.3 minus 0.3. We knew that. And this is depth is 0.2, 1.5 minus 0.2 divided by 2, plus the width is 0.3, the depth is 1.5, the y bar is 1.5 divided by 2, that we know. Okay, so this is equal to 1.4 times 1.2 times 1.4 is 0.392 plus by twice. Sorry, I forget my twice down here. Right, so twice, because you have left and right, the width is 0.3, depth is 1.5, 1.5 divided by 2. So this is left and right web. Okay. 2 times 0.3 times 1.5 times 1.5 divided by 2 is 0.675. So it's equal to 0.392 plus 675 is equal to 1.067 inches cube. Then from here, we can find our, now we realize that this is also equal to our Q max, right? It's much bigger than at point A for sure. So now the shear stress at point C is equal to V over I are the same, right? Q is equal to 1.067. Because it's box beam, you divide by 2, and then you divide by a thickness of 0.3. Okay, this is because of box beam, where you have 2Q, right? So 1.067 divided by 2 divided by 0.3 is equal to 1.778. Okay, so you get 1.778 V over I. And we realize that this is equal to our tau max. Okay, because the shear stress at point A and point B is only 0.98 V over I. Okay. Now I'm now going to do again, but by considering the bottom part. Okay, and the answer should also be the same. Okay, so let's do the bottom part before we determine the value of V. Or yeah, before we before we determine the value of what did the question ask us to find? I can't remember now. It's okay. The shear force, I think. This is embarrassing. Okay. So now I'm going to do the same thing, but we are going to look at by using the bottom part. Okay. So this is still our position of our centroid. So I cover this like what I did before, right? So what we have here is our Q. So we realize that the terminal on the left and the terminal on the right are independent, right? At this position, this is where our point C. So the area to consider is this whole area that I'm shading now. Okay. So we realize that now we have, so again, the shear stress at point C, we have a wide flange analysis. And now Q, this is just Q, okay? And then when we do our thickness is equal to 0.3, okay? So the first moment of area at point C is equal to, so I'm going to call this our flange, and this is our web. So like before, Q of flange plus. Why is the thickness not 0.6? Okay, so Abika, the thickness is all relative to this size over here. So for this case, at point C, the left and right are not connected. So the thickness is always, okay, the thickness is always perpendicular to the shear flow Q. Okay, so this is also this at point C is the point of interest. The thickness is also at 0.3. Abeka, does that make sense to you, or you're still confused over there? Okay. So from here, right? From here, the plus by Q of web. So this is equal to width is 0.7, depth is 0.2. So this is 1.5 minus 0.2 divided by 2. Then plus by the width is 0.3. The depth is 1.5 multiplied by 1.5 divided by 2. 0.7 times 0.2 times 1.4, 0.196 plus by 0.3 times 1.5 times by 1.5 divided by 2, 0.3375. So the first moment of area is 0.196 plus 0.3375 is equal to 0.5335. Okay. So we can't say whether is this tau max or not. It's all relative to the thickness and whether is it box or what. So you find the shear stress at point C is equal to V over I, right? Q is 0.5335. Thickness is, so this is 1 because it is what? It's a wide flange. Okay. And then you have thickness 0.3. Okay. So 0.5335 divided by 3 is equal to 1.778. And this is also equal to a tau max. So whether you derive from the top or from the bottom, if you understand the concept well, the answer will be and has to be the same. Okay, that's how I usually check myself, and I still do that up to today. Okay, if I'm not sure whether my answer is right or wrong, I check with the bottom, and the answer is exactly the same. Right. So now, where does this leave us? So we know that tau max